Hello, and thank you for taking the time to come to my talk at WATI 2024. My name is Josh Myers-Dean, and I'm presenting on our paper, Interactive Segmentation for Diverse Gesture Types Without Context. This is joint work between my institution, CU Boulder, and Adobe Research, and I am graciously supported by funding from the National Science Foundation. And so if you're not familiar with what interactive segmentation is, at a high level, given some user input, typically in the form of clicks, scribbles, lassos, or bounding boxes, we want to segment some region in the image. And typically the users need to provide context on what should and shouldn't be included in our final result. For example, given the sheep, we're going to place a red positive click on the sheep on the left to indicate that we want it included in our final result. And we'll place blue negative clicks on other parts of the image, such as the background or the other sheep, to indicate content that should not be included in the final segmentation. And not only can we do this from just a plain image, but we can also refine previous segmentations and refine them until they meet the specifications for whatever application we're using our final mask for. And then as far as applications go, interactive segmentation has been prevalent in many applications such as image editing, where a photographer might want to select their subject to perform some photometric augmentations, such as adjusting contrast or brightness or saturation, as well as data annotation pipelines, where a user may want to speed up their selection process of different objects that they want to annotate, and also in helping medical practitioners with their downstream diagnostic tasks. While there's been impressive work in interactive segmentation over the past 2 decades, there are a few limitations to existing methods. The first one being that algorithms typically only support one gesture type at a time, such as clicks or rectangles. However, we found that users prefer different types of gestures depending on the region they're selecting. And as a consequence, if a user wants to select different objects in an image with different gesture preferences, they're going to have to do all these different tool switches. Maybe they'll want to click on chocolate chips with using a click tool, or they'll want to scribble on power lines to indicate they want to select them. This could lead to many tool changes just to accomplish a single selection task. In addition, most algorithms require the context of an interaction. So as we saw earlier, indicating content that should or shouldn't be included in a final segmentation, or including parts of an existing segmentation that you want to remove or add to. And so this puts a high cognitive load on the user, or at least we hypothesize it does. And we believe that we could simplify this task. And to simplify this task, we first are going to require all algorithms to support multiple gesture types simultaneously without any knowledge of what gesture type is being employed. Meaning that a user, in theory, could just freeformly draw over the image that they're interested in without having to specify what tool they're using. Moreover, we want to remove the constraint that users need to provide the context of the interaction, such that algorithms should infer the intent of the user when they're selecting an image or selecting a region in an image or refining a previous segmentation. To put this in simple terms, the only input to an algorithm is going to be a marking on an image or on a previous segmentation. And so we exemplify this in this figure here. We have a user, some region of interest, and maybe a previous segmentation. And then we could use any gesture we want. So you could see that we're either circling around the turtle, scribbling on it, drawing a box, or clicking on it. And ideally, we'll get a perfect segmentation in return. To support our novel task, we introduced the DID, or Diverse Interactive Gesture Dataset, which is the first interactive segmentation dataset that provides annotations for multiple gesture types, such as clicks, scribbles, lassos, and rectangles, and also includes pre-computed imperfect previous segmentations to aid in efficient algorithm training. Among these annotations, we support scenarios such as single region, like if you only want to select the TV on the left, region part, if you only want to select the head of the dog, and multi-region, if you want to select, say, 2 cows in a field of cows. In addition to this, we also provide annotations and ground truths for corrections within our pre-computed previous segmentations. We also introduce a new holistic evaluation metric for interactive segmentation that we call the Relative IOU Corrective Evaluation Metric, or RICE for short, to address the issue that existing metrics such as IOU or number of clicks don't capture how much a previous segmentation has been improved or degraded with a new prediction. And so to do this, we measure the relative improvement of a prediction over some previous segmentation to get a score ranging from -1, meaning that we destroyed the segmentation entirely, or 1, that we perfectly improved it. And to put this concretely, say I have this picture of my dog and I want to include his backpack in the final segmentation. So I'll click on his backpack, and if I get some of his backpack in our final segmentation, that would result in a positive rice score, meaning that we improved over the previous state of the segmentation by getting closer to the ground truth. And say that instead of adding to the segmentation, the algorithm thought that we wanted to remove, say, the straps from his harness. This would lead to a negative rice score as we took away content that should have been included in the final segmentation. And finally, we evaluate both state-of-the-art existing interactive segmentation methods as well as newly proposed models by us for the settings of segmentation creation, so just starting from a plain image, and segmentation refinement, where we want to refine some previous segmentation to make it closer to the ground truth. Overall, we find that models that were designed to handle multiple gesture types, such as a proposed methods or segment anything, show superior performance when using different gesture types compared to single gesture models, such as RITM or focal click, which are only designed to support clicks. Additionally, we evaluate these context-dependent algorithms in a setting where we restrict the contents they receive and vary how they receive this context. Overall, we find that these algorithms struggle in refining previous segmentations, while our proposed context-agnostic algorithms show positive performance. And again, thank you for coming to this talk. I hope that you check out our full paper and dataset, which you can do so by following this QR code here. And I hope you have a happy WACB. Thank you.